What is going on, guys? Welcome back. In this video today we're going to implement a machine learning classification algorithm from scratch in Python, namely the k-nearest neighbors classifier. So let us get right into it. Alright, so we're going to implement k-nearest neighbors classification from scratch in this video today, meaning we're not going to use scikit-learn, we're not going to use TensorFlow or any other machine learning library. We're just going to use NumPy so that we can work with arrays efficiently, and we're going to use matplotlib for the visualization. Everything else will be written in core Python and from scratch. So we're going to implement the distance measure from scratch, and we're going to also implement the fit and predict functionality from scratch. Now, one thing that might be interesting to you guys is that there's also a text-based, so a written version of this tutorial you can find on my website, neural9.com, k-nearest neighbors classification from scratch in Python. Now, this post is quite old, so the code that we're going to write in this video today will not be 100% the code of this blog post. It will be more professional today and better code. However, since this blog post exists, I can just explain the mathematics briefly here because I already have basic visualizations and formulas here. So the basic idea of k-nearest neighbors classification is very simple. As the name already says, we're using the k-nearest neighbors, k being a number, a variable, the k-nearest neighbors to determine the class of a new point. So let me just open here the most advanced visualization tool there is, Paint. And let's say we have a data set where we have, I'm going to use now a red brush here. We have a couple of data points here that have the red color as their class, so to say. So they belong to the class red. And then we have some that belong to the class blue, and they're clearly separated in this case. Now, oftentimes in real life, data sets are more mixed, so you will have some red points here, some blue points here. But let's say this is the data set. Now, what a k-nearest neighbors classification algorithm does is it takes a new point, let's say this one here, and it looks at the k-nearest neighbors, meaning it calculates the distance to all these points, to every single point, also the other ones here. And then it takes the k-nearest points, so the points, the k points with the smallest distance, and the class it ends up having is the class that the most points have. So in this case, probably the k-nearest points are this one, probably this one, maybe this one. All of them are red. Now let's say we also have a blue point here. This would not change the result if we're looking at the three nearest neighbors. The three nearest neighbors are this one, and let's say this one. In this case, we have two red instances, one blue instance, so the class of this new point, of this unlabeled point, would be red according to the three nearest neighbors. That's the basic idea, and this is what we're going to implement today. Now, the distance, this is important, is going to be the Euclidean distance. So basically what you use, let me open Paint again. Basically, when you have a point here and you have a point here, the Euclidean distance is just the distance in general. So meaning x and y, basically the square root of x squared plus y squared. So the Pythagorean theorem, that's the basic distance here. And this works for n dimensions. So it doesn't have to work only in 2 dimensions. The formula in general of the Euclidean distance is this one, depending on how many dimensions you have, n dimensions. This is how you calculate it. So you just take the square root of 0.1 and minus 0.2 squared for each axis. So x-axis, y-axis, z-axis, and so on, depending on how many dimensions we have. So very simple, just a Pythagorean theorem in n dimensions, nothing too complicated. And this is what we're going to implement in this video today. So in order to train a k-nearest neighbors classifier, we don't have to do anything because the training is already just the points existing. The actual work happens when you make a prediction, because when you have a bunch of data points, a couple of blue points, a couple of red points, this is already your model, so to say, because you already have those points. It's not like with other machine learning algorithms where you have to train a model and then you have to fit that model and then you use that model to make predictions. The k-nearest neighbors classification model is, so to say, the data itself, because all we need to do is we need to calculate distances to the points, and we can only calculate distances to the points when we have a new point. So we cannot do anything without having a new point to calculate the distances to. Yeah, so that's basically what we're going to do. We're going to start here by importing numpy snp and matplotlib.pyplot splt. By the way, if you don't have these libraries installed, you just go into your command line and you type pip install numpy matplotlib, like this. And then we're also going to use here from collections, this is core Python, we're going to just import the counter so that we can count the most common class in the k nearest neighbors. And what I'm going to do now here is I'm going to artificially define some points. So we're going to say here points equal a dictionary. We're going to have the blue class, which is going to have the following points, 2, 4, 1, 3. I'm looking at my second screen because I want to take the exact same points that I used in the preparation because those are well separated. So those are the coordinates for the blue points. And then we also want to have red points, and the red points are going to be 5, 6, 4, 5, 4, 6, 6, 6, and 5, 4. Now you can also come up with your own points. Those are just some coordinates that are separated. And what we want to classify now is a new point. So we're going to say here new point is going to be equal to 3, 3, for example, which is somewhere in the middle, but probably closer to blue. So this is in 2 dimensions. We're also going to look at an example in 3 dimensions, but we're going to start with a 2D example here. And what we want to do first is we want to have a very simple one-line function that calculates the Euclidean distance between 2 points. And this can be done very easily with NumPy. So this is not a cheating because we're not using NumPy to do to just apply the actual formula. We're just using NumPy so that we can easily do calculations with the array. So what we're doing here is we're taking P, which is 1 point. So let me just define the structure here. Euclidean distance from P to Q. Those are 2 points. Now we want to take every dimension of P and every dimension of Q and get the difference. So basically P minus Q. And we want to square that. Distance, and then we want to sum it up, and you want to take the square root. Now, if you're working with basic Python list, you would have to iterate over all the dimensions. You would have to use loops and stuff like that. With NumPy, we can just do np array. We turn P into an array. Now it's a list. So this is P, for example. This is Q, for example. Or actually, this would be P. This would be Q, for example. We're turning both of them into NumPy arrays. And when you apply subtraction onto a NumPy array, that's not the same thing that happens with lists. So I think when you subtract lists, it's not even supported. But when you subtract one NumPy array from another NumPy array, you subtract the values from all the other values. So P minus Q means every value in P minus every value in Q is the result. And what we want to do with this is we want to say np dot sum. We want to sum up all the differences. We want to square root, we want to square them, and then we want to take the square root of that. Or actually, let me just see, does that make sense? No, if we actually, is this a mistake in my code here? Let me just see how I did it here, Euclidean distance. Actually, I don't think that that's correct, right? Because we're squaring and then we're taking the square root. What we should be doing, as it's written here in the formula, is we should square the distance. So this is actually a mistake in my blog post, so don't read it. We're squaring the actual distance. So we're doing this. We're subtracting. We're squaring that. We're summing that up, and then we're taking the square root. So np square root of np sum. Is that not what I did here, right? So here I have sum of, yeah, this is wrong. This is how you want to do it, because you want to subtract here, you want to square the distance, you want to square the difference, then you want to take the sum of all that, and then you want to do the square root, because if you do the square root of the square, you're just getting the sum, right? So this is not what you want. This is how you calculate the Euclidean distance. And then what we want to do is we want to create a simple classifier. So k nearest neighbors, I'm just going to call it like that, k nearest neighbors. And for the constructor, we don't want to have too many things. We just want to define k, so the nearest neighbors to look at. We're going to set it by default to 3. We're going to say self.k equals k, and self.points are going to be none. So remember, I said training the k nearest neighbors classifier means having points. Points existing is a trained model in this case. So what we want to do here is we want to say fit. We want to provide the training data in this case, so the points, and basically self.points equals points. That's the training. There's not much more that we can do. And then for the predict, this is where the actual work happens. Predicting means calculating the distances between the one new point to predict on, to make a prediction for, between this point and all the other points. So what we want to do here is we want to say predict self and then new point is the input here. And we want to keep track of all the distances. And we're going to then say for category, I don't want to use class because class is a keyword. For category, so for blue and red, what we want to do for category in self.points, we want to say for point in that category, so self.points category, not a string, actually the variable category. So for all blue points, for all red points, what we want to do is we want to get the distance, which we're going to calculate using the Euclidean distance function, between the current point that we're looking at and the new point. And then we want to append to the distances list a list with two elements, the first one being the actual distance and the second one being the class, so the category. Because then we're going to get just the k nearest points with the smallest distances, and then we're going to just look at the categories and sum them up. And this is done by saying categories equal category index 1 to get the actual category, not just the distance. For category in sorted is important. We want to sort the distances. So we sort the distances by distance. So the smallest distances are going to be the first elements. We sort the list, and then we're going to just get the first k instances. So up until self.k. So in this case, we would get the first three instances, the three instances with the smallest distance. Those are the categories. We don't get the full distance. We don't get the full list here. We just get the categories. So we would have blue, 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 or blue, red, blue, whatever. We would just have the categories of the three nearest instances. And then what we want to do is want to say result equals count the categories and return the most common 1, 0, 0 to get the actual result. And then we return the result. And that's basically how you do a k-nearest neighbors classification. So what we're going to do now is we're going to create a classifier, k-nearest neighbors, k equals 3. So basically the default parameter, we don't need to even specify it. And CLF is going to be fit onto the points. Now, it's important, of course, for this particular classifier that the structure looks like this. So if you pass a NumPy array or a pandas data frame, it's not going to be able to handle that. You would have to do some pre-processing for that. But this is also not the focus of this video, to make it compatible with all input types. But what we are going to do now is we're going to print CLF predicts, and we're going to predict the new point. And this gives us blue. Now, this is not very satisfying because we don't see anything. We don't see how it works and all that. So what we're going to do now is we're going to visualize these distances. We're going to visualize the classification using matplotlib. So I'm going to start a new section here, visualize. Let me zoom in a little bit. And we're going to say here, the axis is going to be a new subplot. We're going to set the grid to true with a color of 323232, so gray basically, and we're going to say axis figure dot set face color. We're going to apply a dark theme here. This is basically what I did for the blog post, so this is the theme that we're going to use here, this one. So we're just setting some parameters here. Tick underscore params are going to be, the x-axis is going to have white ticks. The y-axis is also going to have white ticks. And then we're going to plot the actual point. So 4 point in points of category blue in this case. We're going to scatter all these points. So point index 0, coordinate 0 you could say, x coordinate, point y coordinate, and the color is going to be basically a blue, which is going to be 104 DCA. with s equal to 60. I think that's the size. Then we're going to copy that. We're going to paste this. We're going to change this to red. And I'm going to just provide you now ff0000. And then we're going to also have the new point. So we're going to say here, the new class of the point is going to be whatever the prediction says. So in this case, it will be blue. We predict on a new point what class it is. And then we say the color of this new point is going to be basically ff0000 if new class equals red, else it's going to be 104 DC8. And then we just plot this new point as well. So scatter it onto the axis, new point 0, new point 1. Color is whatever the color happens to be based on the class. The marker is going to be a star so that we have a different marker for this new point to be able to differentiate. Then we're going to say s equals 200 and z order is 100, basically just for the placing in the plot. So if it's on top or not, if some other element is in the same area. And then what we're going to do is we're going to draw a dashed line towards each point. So the distance, we're going to visualize the distances. So we're going to use the same loop structure here. I'm going to copy this, but we're not going to scatter. So I'm going to remove this and I'm going to remove this. But for each point in blue, we will say axis plot, and we're going to plot new point 0, new point, not new point 0, sorry, new point 0, point 0. So the x coordinates. And new point 1 to point 1. So the y coordinates. And the color of the line is going to be the blue color. So 104DC8. The line style, as I said, will be dashed. And the line width is going to be thin, so 1. We're going to copy this now down below. The only thing that we're going to change is the color. Everything else stays the same. And then that's basically it. We need to say plt show. We can run this. And if I didn't make any mistakes, I think I forgot some color option, right? We need to say axis.set_face color, because that's the color of the figure, but the face color is something else. And this is going to be black. There you go. So now we have this basic visualization of the k-nearest neighbors classification. We have this new point here. Those are the distances to the individual points. And you can see probably the nearest point is this one, then the second nearest point, probably this one, and then probably this one. So all of them are blue. What you will notice is, of course, that we can force red if we just add enough red points and we set k to the number of all points. So if I have here 1, 2, 3, 4, 5 blue points, 5 red points, if I add one more red point, so I have 6 red points and 5 blue points, and I include all the points, we're of course going to get red as a class. So we can actually do that if you don't believe me. So we're going to add now a new point wherever it is. It can be very far away. Now we have 11 points instead of 10 points, and I can include all of them in the calculation. So I can go and set, where do I create a classifier here? I can say I can set k equal to 11, and this will automatically end up being red just because it looks at all the points. And even though this is super far away, even if all of them were super far away and all of them were super close, all of the blue ones were super close, all the red ones were super far away, it would still get, it would still become red because it just includes all the points, and we have more red points than blue points. So of course it doesn't make sense to just increase the number of k for accuracy here. All right, so that's it for 2 dimensions. Now let's do the same thing for 3 dimensions. All we're going to do now here is we're going to just include a bunch of new, we're going to include an extra dimension. So we're going to include a z coordinate in all these points. So 5, 1, 3, 6, for example, and down below, we're going to say 5, 6, 5, 4, 5, 2, 4, 6, 1, 6, 6, 1, 5, 4, 6, and then maybe 10, 10, 4. Let's just keep this point here. And a new point is going to be 3, 3, 1, for example. Or let's go 3, 3, 4 to have it more in the center. That's a new point. We don't have to change anything about this function. It's still the same because it includes all dimensions. This is a very flexible function. We can use it with 100 dimensions as well. We also don't have to change anything about the classifier because the classifier is also able to work with 100 dimensions. All we need to change is the visualization. So what we need to do now is we need to say, instead of, where's the code? Instead of saying now axis equals PLT subplot, we're going to say figure equals PLT figure. We're going to say figure size equals 1512, for example. And then axis is going to be figure dot add underscore subplot. And we're going to set the projection. This is the important part. I think it would have also worked with the previous structure, but the important thing is that we pass projection equals 3D because now we're working on a 3-dimensional plot and no longer on a 2-dimensional plot. So all we need to change here now is we need to add this index 2 everywhere. So this new dimension, 0, 0, 1, 0, 0, 1, 2. Also, of course, here for the new point. And then, of course, also for the lines. So when we plot a line now, we're plotting it in 3 dimensions. So we need to add a new list here with new point 2 and point 2. And the same thing needs to be done here as well. So new point 2, comma. That should actually be it if I didn't forget anything. And now you can see we have this 3-dimensional plot here where k nearest neighbors classification also works. So you can see, we can draw the lines. It's still blue because those points are just closer. We can also try to move the point. Let me just see what coordinates we have here. Okay, we cannot see the labels because I messed up the color scheme. But I think if we move the point just to higher values, if I say 5, this is a bit too much, 5, 5, and maybe 2 or something. Okay, it's still blue. Why is it still blue? Should it be blue? How many points is it looking at? Okay, guys, so everything we just did was basically stupid because we didn't return the actual distance. So we had a bunch of non-object. It was just counting. We need to, of course, return the square root in order to make a calculation. So everything we did up until now, also in 2 dimensions, was not correct. Now, the results happened to be correct because blue was the correct answer, but it was just by coincidence. But the whole code was actually correct. The only thing that was missing was this return statement here because without returning the actual square root, the return value of the function is none, and it just counts the categories. So whatever you have more of will be the actual class. But now it should be red. There you go. So now it works. And if I move it back to where it was, so 3, 3, 4, I think, it should be probably blue again. There you go. Now it works. Now it makes sense. This also works in 2 dimensions now, and in 4 and 10 and 100 dimensions. But this is how you implement the k nearest neighbors classification from scratch. Alright, so that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and